Welcome to our lecture on climatic regions. Today, we are going to explore one of the most fundamental concepts in physical geography, Koppen's scheme of classification of climate. The most widely used classification of climate was developed by a climatologist named V. Koppen. He noticed a very close relationship between the distribution of vegetation and the climate of a region. By selecting specific average values of temperature and precipitation, he created an empirical classification scheme that maps out these climatic zones across the globe. You might be wondering, what exactly does empirical mean in this context? An empirical approach relies on observation and experience rather than pure logic or theory. For example, logic tells us a stone falls when dropped, but an empirical approach means actually dropping the stone, observing it fall, and recording the data. Koppen didn't just theorize about climate. He used hard, observable data on temperature and rainfall to define his zones. Koppen recognized 5 major climatic groups, labeling them with the capital letters A, B, C, D, and E. 4 of these, A, C, D, and E, delineate humid climates and are primarily based on temperature. The 5th group, B, represents dry climates and is defined primarily by precipitation, or rather the lack of it. Let's break down these capital letters, starting with Group A. This group represents tropical humid climates. The defining metric here is that the average temperature of the coldest month is 18 degrees Celsius or higher. This means these regions never truly experience a cold winter. Next is Group C, which covers warm temperate or mid-latitude climates. For these regions, the average temperature of the coldest month drops below 18 degrees Celsius, but stays higher than -3 degrees Celsius. These areas experience distinct seasons, but generally avoid extreme freezing winters. Moving further toward the poles, we find Group D, the cold snow forest climates. Here, the winters are severe. The defining characteristic is that the average temperature of the coldest month is -3 degrees Celsius or even lower, leading to significant snowfall that persists on the ground. Group E represents the true cold climates, like the polar regions. In these harsh environments, there is no real summer. The average temperature for all 12 months of the year remains below 10 degrees Celsius. Finally, we have Group B, which stands apart from the others. Group B represents dry climates. Instead of being defined strictly by temperature, Group B is defined by moisture. Specifically, the potential evaporation in these regions exceeds the actual precipitation, resulting in arid or semi-arid conditions. To get more specific, Koppen subdivided these major groups using small letters based on the seasonality of precipitation. The letter F means there is no dry season. M stands for a monsoon climate, W indicates a winter dry season, and S indicates a summer dry season. He also used additional small letters to describe temperature severity. The letters A, B, C, and D indicate how hot the summers are or how severe the winters are. Furthermore, the letters H and K are used to specify regions, with H referring to tropical hot regions and K referring to temperate or cooler mid-latitude regions. For the Group B dry climates, Koppen used a different set of subdivisions, employing capital letters instead of small ones. An S is used to denote a steppe, which is a semi-arid region. A W is used to denote a true desert, which is highly arid. Now let's look at the major climatic types that emerge when we combine these letters. In Group A, we have AF, the tropical wet climate with no dry season. AM is the tropical monsoon climate, featuring a short dry season but heavy monsoon rains. And AW is the tropical wet and dry climate, characterized by a distinct winter dry season. In Group C, the warm temperate climates, we see CF, the humid subtropical climate with warm summers and no dry season. CS represents the famous Mediterranean climate, known for its dry, hot summers. CFB is the marine west coast climate, which lacks a dry season and features mild, warm to cool summers. Moving to the colder regions, Group D includes DFB, the humid continental climate with severe winters, and DFC, the subarctic climate where winters are extremely severe. Group E includes ET, the polar tundra with no true summer, and EF, the polar ice cap covered in perennial ice. There is also an H category for highland climates, which are high-altitude areas with permanent snow cover. For the dry climates in Group B, the combinations give us a very clear picture of the landscape. BSH is the subtropical steppe, a low-latitude semi-arid zone. BWH is the subtropical desert, which is low-latitude and highly arid. Moving away from the equator, BSK is the mid-latitude steppe, and BWK is the mid-latitude desert.
Over time, Koppen's original work was refined, leading to the Köppen-Geiger climate classification. This is the most recently updated model, expanding the system into a highly detailed 31-code breakdown that accounts for very specific regional variations in temperature and precipitation.
Let's explore the updated Köppen-Geiger codes, starting with the tropical group. AF is the tropical rainforest, experiencing no distinct seasons and heavy monthly rainfall over 6 centimeters. AM is the tropical monsoon, defined by a seasonal reversal of winds. AW is the tropical wet savanna with a dry winter, while AS is a very rare tropical dry savanna with a dry summer.
For the arid climates, BSH is the hot semi-arid steppe, acting as a drier extension of the savanna. BSK is the cold semi-arid steppe, often caused by continentality or rain shadow effects. BWH represents hot deserts with less than 25 centimeters of rainfall and drastic temperature changes between day and night, while BWK represents cold deserts.
In the temperate group with no dry season, we have CF, the humid subtropical or China type, which gets rain all year with a peak in summer. CFB is the temperate oceanic or British type, also raining year-round but peaking in winter. CFC is the subpolar oceanic, which is a cooler version of the British type. Temperate climates with a dry summer are the Mediterranean types. CSA is the hot summer Mediterranean, famous for hot, dry summers, cool, wet winters, and vegetation like evergreen oaks. CSB and CSC follow the same precipitation pattern, but have warm and cool summers, respectively.
For temperate climates with a dry winter, CWA is the monsoon-influenced subtropical climate, which features long, drier summers. CWB is the subtropical highland climate, found at high altitudes. CWC is the cold subtropical highland climate, with some locations extending into subpolar regions. Moving to the cold continental climates with no dry season, DFA and DFB are humid continental climates that receive rainfall throughout the year, peaking in summer. DFC and DFD represent the subarctic climates, which are notable for having the highest annual temperature ranges on the planet. The cold continental climates can also have a dry summer. DSA and DSB are similar to the humid continental climates we just discussed, but they experience a distinct dry period in the summer. DSC and DSD are subarctic climates that also experience this dry summer phase. Conversely, cold continental climates can have a dry winter, heavily influenced by monsoon patterns. DWA and DWB are monsoon-influenced continental climates. DWC and DWD are monsoon-influenced subarctic climates, where the freezing winters are also remarkably dry. Finally, we reach the polar climates. EF is the ice cap, where the mean monthly temperature never rises above 0 degrees Celsius. ET is the tundra, defined in this model as having not more than 4 months below freezing. Now that we have mapped out the entire Köppen-Geiger classification system, we are perfectly positioned to dive deep into the specific characteristics of the Group A tropical humid climates next. Picking up right where we left off, let's dive into the specific categories of tropical humid climates, designated as Group A. These climates are found hugging the equator, strictly between the Tropic of Cancer and the Tropic of Capricorn. Because the sun is almost directly overhead year-round and the Intertropical Convergence Zone, or ITCZ, hovers over this region, the climate is consistently hot and humid. You won't see wild temperature swings here. The annual range is very low, while rainfall is incredibly high. We divide this group into 3 distinct types: AF, which is tropical wet, AM, which is tropical monsoon, and AW, which is tropical wet and dry. Let's start with the A category, the tropical wet climate, commonly known as the equatorial rainforest climate. The F here stands for no dry season. This climate is tightly confined to a narrow band just 5 degrees north and south of the equator. Think of the lush lowlands of the Amazon, the Congo Basin, and the islands of Malaysia and Indonesia. Interestingly, because the Coriolis force is practically 0 right at the equator, you won't find any tropical cyclones forming here. The air is dominated by maritime tropical masses, meaning it is constantly humid. Temperatures are incredibly uniform, hovering around 27 degrees Celsius year-round. There is simply no winter. When we look at precipitation in the tropical wet climate, it is defined by its daily rhythm. Almost every single afternoon, heavy cumulonimbus clouds build up, resulting in intense thunderstorms.
The annual rainfall is massive, always above 150 centimeters and sometimes pushing 300 centimeters. There is absolutely no dry season here. A unique hallmark of this climate is its double rainfall peaks. Because the ITCZ passes over the equator twice a year, you get maximum rainfall shortly after the spring and autumn equinoxes, specifically in April and October. Conversely, the least wet months are during the solstices in June and December, when the sun is farthest from the equator.
To see how this is tested, let's look at a question from the 2003 UPSC prelims. We have an assertion: areas near the equator receive rainfall throughout the year, and a reason: high temperatures and high humidity cause convectional rain to fall mostly in the afternoons near the equator. Based on what we just discussed, both statements are absolutely true. The intense daily heating of humid air causes it to rise, cool, and fall as convectional rain every afternoon. Therefore, the reason perfectly explains the assertion, making option A the correct answer.
All that heat and moisture creates the perfect environment for luxuriant tropical rainforests. In the Amazon, these dense forests are called selvas. Because there are no distinct seasons, the growing season never stops. Trees don't all shed their leaves or flower at the same time. The forest forms distinct layers. The tallest trees shoot up to 50 meters to form a thick canopy, which blocks most sunlight from reaching the forest floor. Because it's so dark down below, many plants adapt by becoming epiphytes. These are fascinating plants that actually grow on the trunks and branches of taller trees, just to reach the sunlight, pulling moisture right out of the humid air.
Now, here is an interesting paradox. Despite having the densest forests on Earth, many equatorial countries actually import timber. Why? Because commercial extraction is a logistical nightmare. In temperate forests, you might find an entire mountainside of just pine trees, a pure stand. But in the rainforest, biodiversity is so high that you might only find one mahogany tree per acre. It's incredibly inefficient to harvest. Furthermore, tropical hardwoods are extremely dense. Unlike pine, which floats easily down rivers to sawmills, tropical hardwoods sink. This makes transporting the logs out of the deep jungle incredibly difficult and expensive. Human life in the deep equatorial forests is relatively sparse. For centuries, indigenous peoples have lived as hunter-gatherers. Because the forest provides abundant food year-round, there's little need to stockpile for a harsh winter. Some groups practice shifting cultivation, which we'll detail shortly. There's also a microeconomy based on commercial gathering. For instance, tribes in the Amazon collect wild rubber, the Pygmies in the Congo Basin gather nuts, and the Orang Asli in Malaysia harvest cane to make various products. For those who do farm in the rainforest, shifting cultivation, also known as slash and burn, is the most common method. It's a primitive but historically effective way to deal with the jungle. Tribes will cut down a small plot of trees and burn the vegetation. The ash provides a temporary boost of nutrients to the otherwise poor soil. They grow crops there for a few seasons, but once the heavy rains wash the nutrients away and the fertility drops, they abandon the plot to let the jungle reclaim it and move on to clear a new area. The economic landscape changed drastically with European colonization, leading to the plantation boom. Massive tracts of original rainforest were cleared to grow high-value crops for the industrial West. Natural rubber is a massive industry. While it originated in Brazil, today Malaysia and Indonesia are the dominant producers. Cocoa is heavily cultivated in West African nations like Ghana and Nigeria to feed the global chocolate industry. Another massive crop is the oil palm. Originally from West Africa, it is now grown extensively in Indonesia, which supplies significant quantities of palm oil to countries like India. Despite the agricultural wealth, developing equatorial regions is incredibly difficult. The climate itself is a major hurdle. The relentless heat and humidity cause severe physical fatigue and create a perfect breeding ground for diseases like malaria and yellow fever. The moist air easily transmits bacteria. Building infrastructure is equally daunting. Carving roads and railways through dense jungle exposes workers to wild animals, venomous snakes, and tropical diseases. And even when a road is built, the aggressive jungle growth and torrential rains mean maintenance costs are astronomically high. A major ecological challenge of the rainforest is highlighted in this 2011 UPSC question. It asks why a cleared tropical rainforest doesn't regenerate quickly. The answer is A. The soil of the rainforest is actually deficient in nutrients. This surprises many people who see the lush vegetation, but the truth is the torrential daily rains cause severe leaching, literally washing the nutrients deep into the ground where roots can't reach them. The nutrients are locked in the living plants, not the soil. Once you cut the trees down, the soil degrades rapidly, and tall grasses like lawlong take over, choking out new tree seedlings.
Similarly, look at this 2003 assertion reasoning question. The assertion claims that cleared rainforests yield productive farmland that can support intensive agriculture for years without fertilizers. Based on what we just learned about leaching, we know this assertion is completely false. The ash from burned trees only provides fertility for 2 or 3 crop cycles before the soil is exhausted. However, the reason statement that the primary productivity of the living rainforest is very high is true. Therefore, the correct option is D. A is false, but R is true.
Beyond farming, livestock rearing is also severely handicapped here. There's no soft meadow grass. The native grass is tall, coarse, and lacks nutrition. Cattle produce very little milk or beef. In Africa, livestock are also plagued by the tsetse fly, which spreads a deadly disease called ganana. On the flip side, these regions are incredibly rich in minerals: gold, diamonds, copper, and oil. However, this often leads to a resource curse. Mining for cobalt in the Congo or drilling for oil in the Amazon brings wealth, but it causes massive, often irreversible destruction to the fragile rainforest ecosystem. Moving away from the constant rain of the equator, we entered the AM category, the tropical monsoon climate. Found between 5 and 30 degrees latitude, this climate is most famously developed across the Indian subcontinent and Southeast Asia. The defining characteristic here is the seasonal reversal of winds. During the summer, onshore winds blow from the ocean to the land, bringing massive amounts of moisture and often causing floods. In the winter, the winds reverse, blowing offshore from the land to the sea, resulting in a distinct dry season. Unlike the equatorial region, the monsoon climate has 3 very distinct seasons.
Temperatures in the monsoon climate remain warm, with monthly means always above 18 degrees Celsius. Summers can be brutally hot, pushing up to 45 degrees, while winters are mild, usually resting in the low 20s. Precipitation is heavy but highly concentrated. The annual average is around 200 to 250 centimeters. However, local geography can create extremes. Places like Cherrapunji and Mawsynram in India receive a staggering 1,000 centimeters of rain a year. This happens because moisture-laden winds are forced upward by the Meghalaya Hills, a process called orographic lift, and the clouds are funneled between the mountains, dumping massive amounts of rain.
Let's break down the monsoon seasons, starting with the cool, dry season from October to February. During this time, the northeast monsoon dominates. These are dry winds blowing out from the Asian continent, so they bring almost no rain to most of India. But there are 2 major exceptions. First, the Punjab region gets light rain from western disturbances. These are cyclonic storms brought in by the subtropical jet stream, and they are crucial for winter wheat. Second, as the northeast winds blow over the Bay of Bengal, they pick up moisture and dump it on coastal Tamil Nadu in November and December.
This exact mechanism was tested in the 2015 UPSC prelims. Statement 1 defines westerlies as winds blowing between 30 and 60 degrees latitude, which is correct. Statement 2 says the moist air masses causing winter rains in northwestern India are part of these westerlies. As we just discussed, the western disturbances that water the winter cereals in Punjab are indeed carried in by the westerly jet streams. Therefore, both statements are correct, making C the right answer. Following the winter, we enter the hot, dry season from March to mid-June. As the sun shifts north toward the Tropic of Cancer, temperatures skyrocket, often hitting 44 degrees Celsius in parts of India. The land bakes until mid-June, when we experience the burst of the southwest monsoon. This marks the rainy season. The sudden influx of moist ocean air brings torrential downpours, and almost all the year's rain falls in this short window. Finally, by mid-September, the monsoon begins to lose its strength. The rain bands retreat southwards, the skies clear up, and by October, the cycle resets into the cool, dry season. Just outside the main monsoon zones, we find a variation called the tropical marine climate. You'll see this in places like the West Indies, the Philippines, and eastern Brazil. Instead of a seasonal wind reversal, these areas are constantly influenced by onshore trade winds coming off the ocean. Because of this steady supply of moisture, the rainfall is much more evenly distributed throughout the year. There is no harsh dry season. While the steady ocean breeze makes it very comfortable for human habitation, there is a major catch. These warm coastal regions are highly prone to devastating tropical cyclones, hurricanes, and typhoons. The vegetation in monsoon regions adapts to the distinct wet and dry seasons, forming tropical monsoon forests, also known as dry deciduous forests. The key survival mechanism here is shedding leaves. During the long, hot, dry season, broad-leaved hardwood trees drop their leaves to prevent losing precious water through evapotranspiration. Because of this dry period, the forest canopy is much more open and less dense than the equatorial rainforests. In areas that receive less rain, like the rain shadow regions east of the Western Ghats in India, the forest thins out even further into thorny scrubland or savanna. Monsoon climates are home to massive populations, supporting some of the highest population densities on Earth. The primary occupation is subsistence farming, where families grow just enough to feed themselves for the season. Where irrigation is available, farming becomes highly intensive. The forests also provide economic value through lumbering. Myanmar, for example, produces 3/4 of the world's teak. Because teak is incredibly dense and won't float, loggers actually poison or girdle the trees several years before cutting them down. This allows the tree to dry out while standing, making it light enough to float down rivers to the sawmills. To feed these dense populations, much of the monsoon forest has been cleared for agriculture. Rice is the undisputed king of crops here, heavily reliant on the monsoon rains and extensive irrigation networks. In areas where it's too dry or cool for rice, farmers grow subsidiary crops like wheat, maize, and millet. Beyond food, monsoon lands are massive producers of cash crops. 2/3 of the world's cane sugar comes from these tropical regions. The Ganges-Brahmaputra Delta in India and Bangladesh holds a near the Nathoinorn jute production, and cotton remains a vital commercial crop across the subcontinent. When European colonizers arrived, they looked to the cooler monsoonal highlands to establish massive plantations for exotic beverages. Coffee, which originally came from Ethiopia and Arabia, found a perfect home on the eastern slopes of the Brazilian plateau. Today, Brazil produces nearly half the world's coffee. Tea has different requirements. It needs heavy rainfall, but also well-drained slopes so the roots don't rot, along with moderate temperatures. This makes the Himalayan foothills in India and the central highlands of Sri Lanka absolute premier regions for tea cultivation, though it originally hails from China. We mentioned shifting cultivation earlier. Because tropical soils leach nutrients so rapidly, farmers can't just rotate crops. They have to physically move to a new clearing once the soil is exhausted. This practice is so widespread across the tropics that it has many local names. It's called ladang in Malaysia, taungya in Burma, and tamrai in Thailand. In the Philippines, it's kaingin, in Java, huma, and in Sri Lanka, chena. Across Africa and Central America, it's widely known as milpa, and in Northeast India, it is famously referred to as jhum cultivation. Now we transition to the AW category, the savanna, or tropical wet and dry climate. This is literally a transitional zone that sits between the lush equatorial rainforests and the barren hot deserts. It features alternating wet and dry seasons, with the rains arriving during the warm summer months. It's so perfectly represented in Africa that it's often called the Sudan climate. You'll also find vast savannas in South America, known as the Llanos in the north and the Campos in Brazil, as well as across northern Australia and parts of the interior Indian peninsula. In the savanna, rainfall drops significantly compared to the monsoon zones, averaging between 80 and 160 centimeters annually. The rain strictly follows the sun, falling during the summer months. Temperatures are consistently warm, but the absolute hottest time of the year isn't midsummer. It's actually just before the rainy season begins, when the skies are clear and the sun is intense. Another major characteristic of the savanna is the extreme diurnal temperature range. Because the air is often dry, the days get blistering hot, but the heat escapes rapidly at night, making the nights surprisingly cold. The alternating wet and dry seasons in the savanna are driven by the trade winds. During the summer, the ITCZ shifts and brings moisture-laden onshore winds, delivering rain. In the winter, the winds blow offshore, keeping the land dry. Because trade winds are easterlies, meaning they blow from east to west, they drop most of their rain on the eastern coasts. By the time they reach the continental interiors or western coasts, they are dry. In West Africa, these winter winds blow straight out of the Sahara Desert, bringing dry, dusty air all the way to the coast. The iconic savanna landscape is a sea of tall, coarse grass, dotted with short, scattered trees. This grass, sometimes called elephant grass, can grow up to 15 feet tall during the rainy season. But in the dry season, it dies back and turns into highly flammable tinder, making wildfires a natural and frequent occurrence. The trees, like the famous acacias, are tough survivors. They are deciduous, dropping their leaves to save water. They often have thick trunks to store moisture and umbrella-shaped canopies that reduce their exposure to the harsh, drying winds.
This delicate balance of vegetation was the subject of a 2021 UPSC question. It asks what keeps the trees in check, preventing the savanna from turning into a dense forest. The correct conditions are fire, grazing herbivores, and seasonal rainfall. As we noted, the long dry season turns the grass into fuel for frequent fires that destroy tree saplings. Additionally, massive herds of grazing herbivores trample new shoots before they can grow. Therefore, conditions 2, 3, and 4 are the primary factors maintaining the open grassland, making C the correct answer.
Here is another quick check from the 2012 prelims. What is the characteristic climate of the tropical savanna region? Based on everything we've covered, the answer is straightforward. It doesn't rain all year, it doesn't rain only in winter, and the dry season is certainly not short. The defining hallmark of the savanna is a definite dry winter and a wet summer. Therefore, option D is the correct answer.
The savanna is globally famous as the big game country, home to immense animal diversity and massive seasonal migrations driven by the search for water. Human life here is equally adapted to the landscape. In East Africa, the Maasai tribes are nomadic pastoralists. They revere their cattle, keeping them almost entirely for milk and blood, rarely slaughtering them for meat. In contrast, the Hausa people of Nigeria are settled cultivators who farm fixed plots of land. Historically, many of the best Great Highlands were taken over by colonial settlers to establish large-scale plantations and dairy farms. Farming in the savanna is a constant battle against the soil and the sky. The torrential summer rains aggressively leach vital nutrients like nitrates and phosphates deep into the ground, leaving behind poor, iron-rich lateritic soils that struggle to support basic cereal crops. Add in the highly unreliable rainfall and frequent droughts, and subsistence farming becomes very precarious. However, with proper investment, the savanna has immense potential for plantation agriculture. Countries like Kenya and Tanzania successfully produce large-scale cotton, while West Africa has expanded into commercial groundnut and palm oil cultivation. Finally, while the savanna is often called natural cattle country, commercial ranching faces steep hurdles. The native grasses, while abundant, are coarse and lack the high nutritional value found in temperate grasslands. Because of this poor diet, the local cattle varieties yield very little meat or milk, making large-scale exports difficult for most African and South American nations. The major exception is Queensland, Australia, which has used advanced science, selective breeding, and technology to overcome these natural barriers, becoming a massive global exporter of beef and milk. We've now thoroughly mapped out the humid and transitional tropical climates. Next, we will shift our focus to Group B and explore how nature adapts to the arid extremes of the dry climates. Moving right along from our previous climate zones, let's examine the dry climates, which are classified under the letter B in the Koppen system. The defining rule for any dry climate is simple: evaporation exceeds precipitation. This group is broken down into two main biomes, grasslands and deserts. The grasslands include the subtropical savanna, labeled BSH, and the temperate steppe, labeled BSK. The deserts are similarly divided by temperature into hot deserts, like the Sahara, labeled BWH, and temperate or mid-latitude deserts, like the Gobi, labeled BWK. Let's zoom in on the hot desert climate, or BWH. The H stands for low latitude, meaning these are hot. If you look at a global map, you'll notice a distinct pattern. Major hot deserts are almost always located on the western coasts of continents, sitting right between 15 and 30 degrees latitude north and south. Why are they so dry? It's a combination of three main factors. First, they are dominated by offshore trade winds, which blow moisture away from the land, earning them the nickname trade wind deserts. Second, they often sit in the rain shadow of mountain ranges. And third, they are located under subtropical high-pressure cells, where sinking air prevents cloud formation. You are likely familiar with many of these hot deserts. In Africa, we have the massive Sahara in the north, and the Kalahari and Namib deserts in the south. Moving east, there's the Arabian and Iranian deserts, and the Thar Desert bordering India and Pakistan. Australia is largely defined by the Great Australian Desert. Over in North America, the hot deserts go by several regional names, including the Mojave, the Sonoran, the Californian, and the Mexican deserts. Despite the different names, they all share that same BWH climate profile.
Now, if we want to talk about extremes, we have to look at the Atacama or Peruvian desert in South America. It holds the title for the driest place on Earth, receiving less than 2 centimeters of rainfall a year. This extreme aridity is a perfect storm of geographic factors. It sits in the massive rain shadow of the Andes Mountains. It experiences those dry offshore trade winds we mentioned. The moisture-bearing westerlies blow too far south to help. And finally, cold ocean currents driven by the Walker circulation cool the air above the ocean, severely limiting the amount of moisture the air can pick up and bring inland. Shifting our focus to higher latitudes, we find the mid-latitude or temperate desert climate, classified as BWK, where K indicates cold or high latitude. These deserts aren't dry because of subtropical high pressure. They are dry for 2 other reasons. The first is continentality. Deserts like the Gobi are situated on massive plateaus deep within the continental interior, so far from the sea that rain-bearing winds simply run out of moisture before reaching them. The second reason is the rain shadow effect, which is exactly what creates the Patagonian Desert in Argentina, sitting in the shadow of the Andes. Other notable mid-latitude deserts include Ladakh, the Taklamakan in Central Asia, and the Great Basin in the U.S. Regardless of whether a desert is hot or mid-latitude, the universal rule is that they receive less than 25 centimeters of rain annually. When rain does fall, it's rarely a gentle drizzle. It usually arrives as violent thunderstorms that can trigger sudden, dangerous flash floods. Looking specifically at temperatures in hot deserts, there is no true cold season. Summer averages hover around 30 degrees Celsius, driven by clear skies, intense solar radiation, and dry air. In fact, the highest officially recorded temperature on Earth was 56.7 degrees Celsius in California's Death Valley in 1913. Another key feature is the high diurnal range. Because there are no clouds to trap heat, temperatures plummet as soon as the sun sets, sometimes dropping by 25 degrees, and even causing winter night frosts. Mid-latitude deserts, on the other hand, have a very different temperature profile. Because they are located deep inland and sheltered by mountains, they experience extreme continentality. This means their annual temperature range is massive compared to hot deserts. Winters are genuinely severe, with freezing temperatures, icy winds, and frozen rivers. During these cold months, occasional atmospheric depressions might penetrate the continental mass, bringing light rain or snow. Interestingly, when this ice thaws rapidly in the early summer, it can lead to significant flooding in these otherwise arid basins. To survive in these harsh conditions, desert vegetation must be xerophytic, meaning highly drought-resistant. The landscape is dominated by cacti, thorny bushes, wiry grasses, and scattered dwarf acacias. Trees are incredibly rare, usually only appearing as clusters of date palms where abundant groundwater reaches the surface. The soil itself is tough for plants. The lack of moisture means dead organic matter decomposes very slowly, leaving the soil deficient in humus. Furthermore, the intense evaporation draws water to the surface, where it evaporates and leaves dissolved salts behind, increasing soil salinity and forming rock-hard salt pans. So, how exactly do these plants survive? They rely on incredible evolutionary adaptations. Most desert shrubs develop extremely long root systems to tap into deep groundwater, and they grow widely spaced apart so they aren't competing for the same scarce surface moisture. To prevent water loss through transpiration, these plants often have very few leaves, or their foliage is modified to be waxy, leathery, hairy, or needle-shaped. Even the seeds are adapted. Grasses and herbs produce seeds with thick, tough skins that allow them to lie completely dormant in the dry soil for years, just waiting for that one violent thunderstorm to sprout. Human life in the deserts has historically been defined by movement. Nomadic herding and hunting have been the primary ways to survive when resources are spread so thin. For example, the Bedouin Arabs in Arabia, the Tuaregs in the Sahara, and the Gobi Mongols in the Gobi Desert have traditionally lived as nomadic herdsmen, moving their livestock to follow seasonal grazing. In other regions, such as the Kalahari and the Great Australian Desert, indigenous groups like the Bushmen and the Bindaboo have sustained themselves as highly skilled hunter-gatherers, adapted perfectly to their arid environments. However, settled agricultural life is possible in the desert, provided there is a reliable water source. Historically, this meant living near major exotic rivers that flow through the desert but originate in wetter climates. Today, modern concrete dams, like the Aswan Dam on the Nile or dams on the Colorado River, have vastly expanded desert agriculture. Settlements also thrive around oases, which are natural depressions where underground water reaches the surface. Some, like the Tafilalet Oasis in Morocco, are massive. These settlements are often walled to keep out violent dust storms known as samums. Here, the date palm is the king of crops, alongside maize, wheat, and even cotton. Beyond agriculture, deserts have attracted large populations due to their immense mineral wealth. The discovery of resources has literally built cities in the sand. In the Great Australian Desert, towns like Kalgoorlie sprang up around gold mining. The Kalahari is famous for diamonds and copper. In the Atacama, massive mining camps extract caliche, which is processed into sodium nitrate fertilizer, and it's also home to Chuquicamata, the world's largest copper town. North American deserts yield silver, uranium, and copper. And of course, the discovery of vast oil reserves has completely transformed the economies and landscapes of the Saharan and Arabian deserts.
Moving away from the true deserts, we enter the other half of the dry climates, the steppe or temperate grassland climate, labeled BSK. The S stands for steppe. These regions are primarily located deep within the interiors of continents, falling squarely within the westerly wind belt. The defining feature of the steppe is that it is practically treeless. This lack of trees is driven by the same factors that cause mid-latitude deserts: extreme continentality, where rain-bearing winds simply dry out before reaching the interior, and the rain shadow effect from coastal mountain ranges blocking incoming moisture.
Because these grasslands are found all over the world, they go by many different local names, though the climate is essentially the same. In Eurasia, the vast stretch from the Black Sea to the Altai Mountains is simply called the steppe. In Hungary, it's the pustas. In North America, the vast plains between the Rockies and the Great Lakes are the prairies. In South America, specifically Argentina and Uruguay, they are the pampas. South Africa has the veld, divided into the more tropical bushveld and temperate highveld. Finally, Australia has the Downs, and New Zealand has the Canterbury Plains.
The climate of the steppes is highly continental, meaning it experiences significant temperature extremes. Summers are quite warm, averaging 18 to 20 degrees Celsius, while winters are bitterly cold. However, in the southern hemisphere, the land masses are narrower, allowing for more maritime influence, which makes their summers much less severe. As for precipitation, the steppes receive an average of 45 centimeters annually, sitting right in that sweet spot between desert and forest. The heaviest rains usually arrive in late spring and early summer. During the winter, occasional depressions from the westerlies bring light precipitation, which falls as snow.
The vegetation here is unsurprisingly dominated by grass. Unlike tropical savannas, steppes are virtually treeless. The grasses here are shorter, but they are incredibly nutritious, and their growth isn't abruptly halted by seasonal droughts in the same way tropical grasses are. In areas with richer soil and reliable rain, like the famous Black Earth or Chernozem regions of Ukraine, the grass is lush. In drier continental interiors, the grass becomes wiry and sparse, better suited for ranching than farming. Trees only really appear naturally in transitional zones closer to the poles, or when farmers plant double rows of them to act as windbreaks against the relentless steppe winds. Animal diversity is relatively low, historically dominated by grazing herds and horses.
Economically, the temperate grasslands are powerhouses. The flat level terrain is absolutely perfect for extensive, fully mechanized agriculture. Regions like the North American prairies have been plowed up to become the granaries of the world, producing massive amounts of wheat and maize. Where the land is slightly drier, pastoral farming takes over. Natural grasses are often replaced with highly nutritious alfalfa to support massive cattle and sheep ranches. The invention of refrigerated ships in the 19th century turned these regions into global exporters of meat and dairy. Unfortunately, this intense agricultural development has led to the near disappearance of traditional nomadic herding, as tribes like the Kazakhs were forced to settle and their lands were converted into farms.
Let's look at how this breaks down regionally, because each grassland has its specialty. The prairies are famous for vast wheat fields and cattle ranches. The pustas in Europe utilizes its rich black soil for wheat and sugar beets. Down in South America, the Pampas economy relies heavily on alfalfa-fed cattle for beef and dairy, alongside wheat exports. In Australia and New Zealand, the Downs and Canterbury Plains are world-renowned for sheep rearing, particularly merino sheep for high-quality wool. And in South Africa, the veldts are major producers of maize, alongside livestock rearing.
Now, we transition to the sea climates, starting with the Mediterranean climate, classified as CS. The C stands for warm temperate, and the S is the crucial part. It means dry summer. You might also hear this called the warm temperate western margin climate. The absolute defining characteristic of the Mediterranean climate is its inverted rain pattern. It has warm, completely dry summers and cool, wet winters. This unique pattern is caused entirely by the seasonal shifting of the westerly wind belts as the Earth tilts on its axis. This climate is highly specific in its location. It's strictly confined to the western edges of continents, between 30 and 45 degrees latitude north and south. There are only 5 major regions in the world that experience this. The largest, of course, is the basin of the Mediterranean Sea itself. Then we have central Chile, which actually represents the most perfectly developed form of this climate. It's also found in California, around San Francisco and Los Angeles, at the very southwestern tip of Africa near Cape Town, and in the southern and southwestern corners of Australia, an area sometimes called Swanland.
Let's break down exactly why the seasons behave this way. During the summer, the wind belts shift poleward. This pushes the rain-bearing westerlies away, leaving the region under the influence of offshore trade winds. Because these winds blow from the dry inland areas toward the sea, they bring zero moisture, resulting in clear skies, hot temperatures, and a severe risk of wildfires. But in the winter, the wind belts shift back toward the equator. Now the onshore westerlies hit the coast, bringing cyclonic rain systems directly from the ocean. This rain doesn't fall as a constant drizzle. It usually arrives in infrequent torrential downpours that can cause destructive flash floods in mountainous areas.
Plants here face a brutal challenge. They must survive a prolonged, bone-dry summer. Therefore, Mediterranean vegetation is xerophytic. Trees are widely spaced with small, leathery leaves to minimize evaporation, meaning these forests offer very little shade. In the most favored areas, you'll find open woodlands of evergreen oaks, like the valuable cork oak with its massive fire-resistant trunk. In Australia, eucalyptus dominates, while California boasts the giant redwoods. You'll also find evergreen conifers like pines and cypresses. However, the most common vegetation by far is dense, drought-resistant bushes and shrubs. Interestingly, grass struggles here because the rain only falls in the cool winter when growth is slow, making the grass wiry and unsuitable for cattle rearing. Because cattle rearing isn't viable, Mediterranean agriculture focuses heavily on crops, earning these regions the title of the world's orchard lands. They account for a staggering 70% of global citrus fruit exports. Citrus fruits like oranges, lemons, and olives are perfectly adapted here. Their thick, leathery skins prevent water loss, and the trees have incredibly long taproots to survive the summer drought. The long, cloudless summers are exactly what's needed to ripen the fruit to perfection. Alongside citrus, farmers grow deep-rooted nut trees like walnuts and almonds, and cultivate winter cereals like wheat and barley.
Finally, we cannot discuss the Mediterranean without mentioning viticulture, or grape cultivation. This is a deeply traditional occupation here, with these regions producing 3/4 of the entire world's wine supply. In fact, 85% of all grapes grown in these climates are destined for winemaking. Economically, these areas are massive exporters of fruit and wine, though they have to import dairy due to the lack of pasture. Beyond agriculture, the reliable, clear summer skies and stunning landscapes make tourism a massive economic driver, drawing millions to ancient cities and coastal resorts. We'll see how this compares to the warm, temperate eastern margin climate next. Picking right up from our previous discussion on climate zones, let us shift our focus to the warm, temperate eastern margin climate. You will find this climate situated between 20 and 35 degrees latitude in both the northern and southern hemispheres, strictly on the eastern coasts of the continents. Because of its location in the subtropics, it is frequently referred to as the humid subtropical climate. Depending on the specific geographic influences, this climate branches into 3 distinct variants: the China type, the Gulf type, and the Natal type. Let us break down each one. The first variant is the China type, observed mostly in central and northern China and southern Japan. In the summer, intense heating over the continental interiors, like Tibet and the desert regions, creates a massive low-pressure zone. This draws in the tropical Pacific airstream, creating the southeast monsoon. Unlike India, this monsoon doesn't burst suddenly, but it does bring typhoons in late summer. Conversely, winter sees intense high pressure over Siberia. This forces a continental polar airstream outward as the northwest monsoon, making the winters bitterly cold and very dry, though windward slopes do receive considerable snow. Moving over to North America, we find the Gulf-type climate in the southeastern United States, right along the Gulf of Mexico. Here, summer heating of the continent pulls in moisture-laden air from the cooler Atlantic Ocean. The key difference between the Gulf type and the China type is that the Gulf type does not experience a complete seasonal wind reversal. The monsoonal characteristics are much less intense because the pressure differences aren't as extreme as those in Asia. However, this region is highly susceptible to severe tropical cyclones, known locally as hurricanes, particularly in September and October.
In the southern hemisphere, we encounter the Natal-type climate. You will find this in New South Wales in Australia, the Natal region of South Africa, and the Parana, Paraguay, Uruguay basin in South America. What sets the Natal type apart is that it receives rainfall all year round from the onshore southeast trade winds. Because the land masses in the southern hemisphere are much narrower, the maritime influence dominates, completely eliminating the monsoonal elements. So to compare, the China type is highly monsoonal, the Gulf type is slightly monsoonal, and the Natal type is entirely non-monsoonal.
Looking at the general climate of the warm temperate eastern margin, it's characterized by warm, moist summers and cool, dry winters, though winters in the Natal type remain moist. Temperatures generally range between 4 and 25 degrees Celsius, kept relatively moderate by the nearby oceans. However, occasionally, cold air from the polar vortex can sweep down from the continental interiors, dropping temperatures to freezing. Rainfall is quite generous, ranging from 60 to 150 centimeters, distributed fairly evenly throughout the year. This comes from convectional or orographic rain in the summer and cyclonic depressions in the winter.
Because the perennial plant growth here is not halted by a severe dry or cold season, this climate supports incredibly luxuriant vegetation. In the lowlands, you will find a mix of evergreen broadleafed forests and deciduous hardwoods. As you move up into the highlands, these give way to valuable softwood conifers like pines and cypresses. The timber from these regions is highly valuable. China and Japan harvest oak and camphor. South America yields the Parana pine and the incredibly hard quebracho wood, literally meaning axe diker. Australia is famous for its eucalyptus, while Natal features palm trees and the Gulf states have extensive deciduous forests. This generous rainfall makes these regions agricultural powerhouses, supporting incredibly dense populations. The cropping patterns vary by region. Southeastern China focuses on rice, tea, and mulberries for silk production, though sericulture is declining. The U.S. Gulf states grow maize, cotton, and tobacco. Natal relies heavily on sugarcane, while South America produces coffee, maize, and dairy. Let's look closer at monsoon China. It produces a staggering 1/3 of the world's rice. The warm, wet climate and moisture-retentive alluvial soils are perfect for paddy cultivation. Because flat land is scarce, farmers ingeniously terrace the hill slopes. However, despite the massive yield, China's huge population consumes almost all of it, leaving very little for export. In contrast to China, the Gulf states of the USA historically had low population pressure, which encouraged export-driven agriculture. Corn, or maize, is a massive crop here. The humid air, sunny summers, and heavy showers are perfect for it. The famous Corn Belt spans Nebraska, Iowa, Indiana, and Ohio. Corn is favored because of its prolific yield, producing almost twice as much starch per acre as wheat. Interestingly, while the U.S. produces over half the world's corn, it exports very little of the raw crop. Instead, the corn is used domestically to fatten cattle and pigs. These animals are then sent to massive meatpacking plants in Chicago and Cincinnati to be processed and exported as meat products. The Gulf-type climate is also arguably the best in the world for growing cotton. It provides a long, hot growing season with 200 frost-free days, allowing the crop to mature slowly over 6 months. However, the immediate coastal Gulf lands receive too much rain, which damages the cotton lint, so those areas focus on citrus and sugarcane instead. Commercial cotton is concentrated in the Mississippi floodplains. A major historical challenge here has been the boll weevil, a devastating pest that actually forced the cotton belt to migrate westward. Alongside cotton, tobacco is a major cash crop. Native to America, crops like Virginia tobacco thrive in the humid, warm, well-drained soils of the eastern states, supplying half of the international tobacco trade. Looking at agriculture in the southern hemisphere, the coastlands of Natal are dominated by cane sugar, while the interior grows cotton, tobacco, and maize. In South America, the agricultural activity is dictated by rainfall. Where rainfall is under 120 centimeters, you find extensive natural grasslands, perfect for rearing cattle and sheep for meat and wool. Where rainfall exceeds 120 centimeters, the landscape shifts to forests, and the economy shifts to harvesting yerba mate, lumbering Paranal pine, and growing sugar. Finally, in eastern Australia, the giant eucalyptus forests have largely been cleared by European immigrants to make way for intensive dairying, making New South Wales the country's chief source of milk, butter, and cheese. Now, let us transition to a completely different climate zone, the cool, temperate western margin climate, commonly known as the British-type climate. Because of its strong oceanic influence, it's also called the Northwest European maritime climate. These regions are under the constant influence of the westerlies all year round and experience frequent frontal cyclonic activity. Geographically, you'll find this in Northwest Europe, the coastlands of British Columbia in North America, where the high Rockies block the winds from moving inland, and in the southern hemisphere in places like southern Chile, Tasmania, and New Zealand. The British-type climate is highly favorable for maximum human output. The temperatures are moderate, generally between 5 and 15 degrees Celsius. Summers are warm, but the winters are abnormally mild. This mildness is largely thanks to the warming effect of ocean currents like the North Atlantic Drift. Precipitation falls throughout the year, usually peaking in winter due to passing cyclones. In places like New Zealand, the westerlies hit the mountains, causing heavy orographic rainfall on the windward side and leaving the eastern Canterbury Plains in rainchadel. Notably, unlike the tropics, this climate features 4 very distinct seasons: winter, spring, summer, and autumn.
The natural vegetation of the British-type climate is the deciduous forest. These trees have developed a brilliant adaptation. They shed their leaves in the autumn. This prevents snow from accumulating on broad leaves and breaking the branches, and protects the tree from severe winter frost. Common species include oak, elm, ash, birch, beech, and poplar. In the wetter areas, you will find willows, which you might know are used to craft high-quality cricket bats. As you move higher up the mountains where the temperatures drop and soils thin out, these deciduous trees are replaced by hardy conifers. Economically, the lumbering industry here is quite profitable. Unlike the tangled equatorial jungles, these deciduous forests grow in pure stands with sparse undergrowth, making logging and transportation highly economical. The hardwoods are used for industry, while mountain conifers supply the paper and pulp industries. Beyond lumber, these regions are some of the most highly industrialized in the world. Rather than relying solely on agriculture, countries like Britain, France, and Germany leverage their mineral resources to produce machinery, chemicals, and textiles. Germany is a global hub for the automobile industry. Meanwhile, Denmark and New Zealand have industrialized their dairy production, and Tasmania is world-renowned for its merino wool.
Because Northwest Europe is so densely populated and highly industrialized, the region actually has no surplus food for export. It is a net importer of crops like wheat. However, domestic agriculture is highly specialized. Market gardening is huge here. There is a massive urban demand for perishable goods like fresh vegetables, eggs, and milk. This requires rapid transport, leading to truck farming in the US, and the use of high-speed boats to rush produce from Tasmania to mainland Australia. Farmers also practice mixed farming, cultivating crops on plowed land while keeping animals on grass meadows. They grow wheat for local food and high-quality barley specifically for breweries and whiskey distilleries.
Livestock is a cornerstone of the British-type climate economy. The mild, moist conditions are absolutely ideal for intensive dairying. The Netherlands is famous for cheese, while Denmark and New Zealand produce world-class butter. Excess milk is condensed or evaporated for global export. For meat, Argentina and Australia focus heavily on beef cattle. Interestingly, in mixed farms, pigs and poultry act as scavengers, eating agricultural leftovers. Denmark uses skimmed milk, a byproduct of butter, to feed pigs, creating a massive bacon export industry. Finally, sheep are reared for both wool and mutton. While Britain exports elite pedigree sheep breeds, New Zealand utilizes the rain shadow of the Canterbury Plains to raise sheep, exporting chilled lamb across the globe.
2 other crops play a vital role in this climate: potatoes and sugar beet. Potatoes are a staple food for millions here, supplementing wheat. They are incredibly valuable because they yield far more starch per acre than any cereal and can grow in a variety of soils. Then we have beet sugar, which is cultivated almost exclusively in northwestern Europe and parts of the US. The root is crushed for sugar, while the leafy tops feed livestock. Interestingly, extracting sugar from beets really took off during the Napoleonic Wars, when military blockades cut Europe off from tropical cane sugar imports.
Moving further north, we encounter the cool, temperate eastern marine climate, widely known as the Laurentian type. Think of this as a transition zone. It is intermediate between the moderate British climate we just discussed and the extreme, freezing taiga climate further north. It blends maritime and continental features. Crucially, the Laurentian climate exists only in the northern hemisphere. You'll find it in eastern Canada, the northeastern US, and across eastern Asia in Siberia, northern China, and Japan. It is completely absent in the southern hemisphere because the continents taper off and become too narrow, meaning the oceanic influence is too strong to allow for continental climate extremes.
In the Laurentian climate, winters drop below freezing with significant snowfall, while summers can be surprisingly warm, reaching up to 25 degrees Celsius, and are quite wet. Precipitation falls year-round, but peaks in the summer. However, the 2 main regions behave slightly differently. In North America, the moisture is boosted by the Great Lakes and the warm Gulf Stream. Where the Gulf Stream meets the cold Labrador Current near Newfoundland, it creates incredibly dense fogs. The Asiatic region, conversely, has a rainfall pattern resembling a monsoon. Winters are extremely dry and cold, driven by Siberian winds, while summers are exceptionally wet. Japan also experiences heavy fogs where its own warm and cold currents, the Kuroshio and Oyashio, collide.
The heavy rainfall and damp air of the Laurentian climate heavily favor forest growth. There is a distinct dividing line around the 50th parallel north. North of 50 degrees, you find vast, pure stands of coniferous trees like fir and spruce. South of 50 degrees, deciduous trees like oak, maple, and birch take over. Economically, lumbering is massive here. Eastern Canada is the absolute heart of the global timber and wood pulp industry, utilizing the St. Lawrence River for export. Agriculture is somewhat restricted by the long, severe winters, but North American farmers have successfully adapted by focusing on dairy farming, and specific microclimates like the Annapolis Valley in Nova Scotia are world-renowned for apple orchards.
While agriculture is limited, the Laurentian regions dominate in another sector, fishing. Off the coast of Newfoundland lies the Grand Banks, the largest and most productive fishing ground on Earth. This incredible productivity is caused by the mixing of the warm Gulf Stream and the cold Labrador Current over gently sloping, shallow continental shelves. This mixing creates the perfect environment for microscopic plankton to explode in numbers, which in turn feeds millions of fish. The industry here is highly advanced, utilizing mechanized trawlers with onboard refrigeration. The Port of St. John serves as the bustling headquarters not just for Canadian fleets, but for international vessels from Europe and Japan as well. Across the globe, the Northwest Pacific surrounding Japan is another premier fishing ground. Fishing is absolutely vital to Japan's survival. Why? Because 80% of Japan's land is mountainous and unsuitable for agriculture or livestock pasture. With a scarcity of meat, fish became the primary protein. Japan has heavily invested in this, building massive ports like Hakodate and sending fleets as far as the Antarctic. They have also pioneered aquaculture, cultivating seaweed for food and fertilizer, and harvesting cultured pearls from oysters. Geographically, Japan is blessed with indented coastlines for safe ports and highly productive waters where the warm Kuroshio and cold Oyashio currents mix. I've mentioned ocean current mixing zones a few times now, but why exactly do they create such incredible fishing grounds? It all comes down to phytoplankton, the microscopic plants that act as the grass of the sea. To photosynthesize, phytoplankton needs sunlight, which is only at the surface, and nutrients. The problem is, as organisms die, they sink, taking those vital nutrients down into the dark, deep ocean, where phytoplankton can't reach them. This is where mixing zones and upwellings come in. When cold and warm currents collide, or when cold surface water sinks at high latitudes, it forces the deep, nutrient-rich water back up to the sunlit surface. This constant recycling of nutrients fuels massive plankton blooms, which feeds the entire marine food web. These phytoplankton are the absolute foundation of ocean life. The most predominant types you will find in these nutrient-rich waters are diatoms, which are a type of unicellular algae, and dinoflagellates. You also have coccolithophores and various forms of cyanobacteria, or blue-green algae. Without these microscopic producers thriving in the mixing zones of the Laurentian climate, the massive fishing economies of Canada and Japan simply wouldn't exist. Now that we understand the dynamics of the cool temperate margins, we are ready to move even further poleward. In our next segment, we will explore the freezing extremes of the taiga, or boreal climate. Let's examine the taiga climate, which is also known as the Siberian climate, the cool temperate continental climate, or the continental subpolar climate. This climate zone is located just below the Arctic Circle, roughly between 50 and 70 degrees north latitude. Looking at the global distribution of forests, temperate coniferous forests actually cover the highest percentage of forest area in the world, accounting for nearly 34% of global forest cover. The taiga climate is unique because it is found exclusively in the northern hemisphere. This is due to the massive east-west extent of landmasses there. As we move poleward, it merges into the Arctic tundra, and moving equatorward, it fades into the steppe climate. It is completely absent in the southern hemisphere because the landmasses narrow significantly at high latitudes, leading to a strong oceanic influence that prevents this continental climate from forming. Geographically, this continuous belt stretches across central Canada, parts of Scandinavia, and most of central and southern Russia. This brings us to a question from the 2003 UPSC prelims. It asked which forest type covers the highest percentage of forest area in the world. The options were temperate coniferous, temperate deciduous, tropical monsoon, or tropical rainforests. As we just discussed, at a global scale, temperate coniferous forests cover the highest percentage, making option A the correct answer.
Interestingly, if we look just at India, tropical moist deciduous forests hold the highest percentage. Let's look at the temperature profile of the taiga. Summers are brief, but surprisingly warm, reaching 20 to 25 degrees Celsius. However, winters are notoriously long and bitterly cold, often plunging 30 to 40 degrees below freezing. Because these regions are deep inland, away from the moderating effects of the ocean, they experience extreme continentality. This results in the greatest annual temperature range in the world, sometimes a 50 to 60 degree difference between summer and winter in Siberia. In fact, Verkhoyansk in Russia once recorded a staggering minus 67 degrees Celsius. During these severe winters, nearly all rivers in Russia freeze over. The Volga, for instance, is typically ice-covered for about 150 days a year. Interestingly, despite the extreme cold, permafrost, a permanently frozen subsurface layer, is generally absent here. This is because the heavy snow cover acts as a poor conductor of heat, effectively insulating and protecting the ground from the severe cold above. The region is also battered by violent cold polar winds, known as blizzards in Canada and the Boran in Eurasia. Moving on to precipitation, the deep interiors of the taiga lack any maritime influence. Typical annual precipitation is relatively low, ranging from 38 to 63 centimeters. It is fairly well distributed throughout the year, but there is a distinct summer maximum due to convectional rains. In the winter, moisture is primarily brought in by frontal disturbances, and naturally this precipitation falls entirely as snow. Because of the low moisture availability, the predominant natural vegetation in the taiga is the evergreen coniferous forest. These trees are perfectly adapted to survive with very little water. The four major species of conifers you will find dominating this landscape are pine, fir, including Douglas and balsam fir, spruce, and larch. The greatest single continuous band of these coniferous forests is the taiga in Siberia. In fact, taiga is simply the Russian word for coniferous forest. In Europe, similar forests dominate Sweden and Finland, with smaller patches in high-altitude areas of Germany, Poland, and Switzerland. In North America, this massive greenbelt stretches all the way from Alaska, across Canada, and into Labrador. In the southern hemisphere, because the climate zone doesn't exist at sea level, coniferous forests are restricted entirely to high mountainous uplands in places like southern Chile, New Zealand, Tasmania, and Southeast Australia. Coniferous forests have some fascinating survival characteristics. They grow in moderate density and are incredibly uniform. Almost all conifers are evergreen, meaning they don't replace all their leaves annually like deciduous trees. A single needle can stay on the tree for up to 5 years. Their iconic conical shape and sloping branches are an evolutionary design to prevent heavy snow from accumulating and snapping the branches, while also offering little resistance to violent winds. They store food in their trunks, protected by thick bark. To survive the warm summers without losing too much water, their leaves are small, thick, leathery, and needle-shaped, which drastically reduces transpiration. Beneath the canopy, the soils of the coniferous forests are quite poor. They are excessively leached and highly acidic. Because the trees are evergreen, they drop very few leaves, and the cold climate means the rate of decomposition is incredibly slow, resulting in low humus content. Consequently, there is almost no undergrowth, a situation worsened by the lack of direct sunlight and the very short summer growing season. While conifers can grow at high elevations, like just below the snowline in the Himalayas, they cannot survive on very steep slopes where soil is immature or non-existent, such as the southern slopes of the Greater Himalayas. Economically, much of the northern coniferous forests remain untouched due to their extreme remoteness. Agriculture is practically impossible in this subarctic climate. Instead, trapping has historically been a major economic activity. Hunters in Canada and Eurasia trap fur-bearing animals like the muskrat, ermine, mink, and silver fox. The severe cold is actually an economic advantage here, as it increases the quality and thickness of the animal's fur. Today, to ensure a steady supply without overhunting, many commercial fur farms have been established in Canada and Siberia. The single most important occupation in the taiga is lumbering. The vast, seemingly endless reserves of softwood coniferous trees provide the perfect foundation for a massive lumber industry. Historically, contract laborers, known as lumberjacks, would temporarily move into the forests to fell trees, though today this process is highly mechanized. Once felled, the softwood logs are easily transported by simply floating them down the rivers to sawmills located downstream. Once at the sawmill, these logs are processed into timber, plywood, and other construction materials. A massive portion of this timber is pulped, using chemical and mechanical means to create wood pulp, the primary raw material for paper and newsprint. While the US is a leader in paper, Canada alone accounts for almost half of the world's total annual newsprint production. Softwood is also used to make matches, particularly in Sweden, and its byproducts yield chemicals like rayon, turpentine, varnishes, and dyes. Because its industrial applications are so valuable, very little softwood is wasted by burning it as fuel.
Several factors make lumbering highly successful in the taiga. First is the sheer abundance of softwood in Russia, North America, and the Fennoscandian countries, coupled with massive global demand for construction and paper. Second, unlike tropical rainforests, which have thousands of mixed species, the taiga has very limited species, mostly pine, spruce, fir, and larch. Time and money. Logistics also play a huge role. The snow-covered ground in winter provides a smooth surface, making logging and haulage relatively easy. Lumbering is usually done in winter when the tree sap is in the ground, making the wood lighter. The logs are dragged to the frozen rivers, and when the ice thaws in the spring, the rivers naturally transport the logs downstream to the sawmills. Additionally, the mountainous uplands of North America and Europe provide cheap hydroelectricity, which is harnessed to power the massive sawmills.
Moving further poleward, we transition from the taiga into the tundra climate, designated as ET. This climate is found north of the Arctic Circle and south of the Antarctic Circle. It primarily covers the lowlands, including the coastal strips of Greenland, the barren grounds of northern Canada and Alaska, and the Arctic seaboard of Eurasia. In contrast, the true ice caps are confined to highlands and massive land masses, like Greenland and Antarctica, where the ice can be up to 3,000 meters thick.
The tundra is an incredibly harsh environment. The mean annual temperature is exceptionally low, with midwinter temperatures plummeting 40 to 50 degrees Celsius below freezing. Summers are fleeting, with normally no more than 4 months rising above the freezing point. Because of the Earth's axial tilt, these regions experience weeks of continuous darkness in winter. The ground remains solidly frozen, and violent blizzards can reach velocities of 130 miles an hour. Precipitation is minimal and falls almost entirely as snow and sleet, with convectional rainfall being completely absent.
Because of the frozen ground and extreme cold, there are absolutely no trees in the tundra. Vegetation is restricted to the lowest forms, such as mosses and lichens. Along the slightly milder coastal lowlands, hardy grasses and reindeer moss provide vital pasturage for reindeer. During the brief summer thaw, the landscape briefly transforms as berry-bearing bushes and Arctic flowers bloom, attracting migratory birds that come to feed on emerging insects. The tundra is also home to resilient mammals like wolves, Arctic foxes, musk oxen, and lemmings, while penguins exclusively inhabit the Antarctic regions in the south.
Human activity in the tundra is sparse and largely confined to the milder coastal areas. The indigenous people, such as the Eskimos in Greenland, northern Canada, and Alaska, have traditionally lived a semi-nomadic life, perfectly adapted to the cold. During the brutal winters, they historically lived in compact, well-insulated igloos. Their diet is heavily reliant on the sea, consisting primarily of fish, seals, walruses, and occasionally polar bears, as agriculture is entirely impossible.
In recent years, the Arctic region has seen significant development, driven almost entirely by the discovery of valuable minerals. New settlements have sprung up around mining operations, gold and petroleum in Alaska, copper and iron ore in Canada, and massive iron ore deposits in Sweden that support a prosperous metallurgical export trade. To support this, new railway lines have been built, and new ports on the Eurasian Arctic seaboard now ship timber and fur. Furthermore, modern icebreakers have made previously frozen seas navigable for commercial shipping.
Finally, we reach the most extreme cold climate, the polar ice cap climate, designated as EF. Here, not a single month of the year has a mean temperature above 0 degrees Celsius. Consequently, the ground is covered by permanent ice sheets, and there is absolutely zero vegetation. This climate dominates Antarctica, inner Greenland, and the northernmost islands of Canada and Russia. The key distinction between the ice cap and the tundra is that the tundra experiences a brief summer above freezing, which melts the surface ice, whereas the ice cap remains frozen solid year-round. Let's test our knowledge with some previous UPSC prelims questions. In 1995, a question provided a climate graph showing high, uniform temperatures around 27 degrees Celsius year-round and high rainfall exceeding 6 centimeters every single month. Because there is no distinct dry season and temperatures are consistently high, this perfectly describes the equatorial rainforest, or rainy tropical climate, making option B the correct answer.
In 1998, a table showed temperatures ranging from about 4 degrees in winter to 28 degrees in summer, with moderate rainfall peaking in the summer months. We can eliminate equatorial and monsoon types because their rainfall exceeds 150 centimeters, and hot desert because its rainfall is too low. The moderate rainfall with a summer maximum and this specific temperature range points directly to the humid subtropical, or China-type climate.
A 1999 question provided data showing rainfall throughout the year, but with a distinct maximum in the winter months, alongside mild temperatures ranging from 6 to 15 degrees Celsius. While China and Laurentian types have summer rainfall maxima, the British, or West European type, is characterized by year-round rain with a winter maximum due to cyclonic activity. Therefore, option C is correct.
Another 1999 question asked to match timber types with countries. Cedar is an evergreen highland conifer found in places like Mexico. Douglas fir is a classic evergreen conifer typical of Canada. Mahogany is a tropical evergreen hardwood famous in Honduras. And teak is a tropical deciduous hardwood heavily associated with monsoon regions like Myanmar. Thus, the correct matching code is A3, B2, C4, D1.
In 2001, a climate table showed an average temperature of 12.8 degrees and rainfall of about 55 centimeters. The defining feature here was the rainfall distribution, almost zero rain during the summer months of June, July, and August, but heavy rain in the winter months of December and January. This classic pattern of dry summers and wet winters is the hallmark of the Mediterranean climate.
A 2002 question asked to identify correct statements. Statement 1 is false because equatorial rainforests have no distinct seasons. Statement 2 is false because the Mediterranean region receives rain in winter, not summer. Statement 3 is true. The China-type climate does experience rainfall throughout the year. Statement 4 is also true, as tropical highlands show vertical zonation of climates based on altitude. Therefore, only statements 3 and 4 are correct. Moving to 2010, a question described an area at 400 meters altitude with consistently high temperatures, around 31 degrees maximum and 21 degrees minimum, accompanied by heavy rainfall every single month. This lack of temperature variation and continuous heavy rain is the exact definition of a tropical rainforest climate, making option D the correct choice. Another 2010 question asked to identify a region characterized by a warm and dry summer, a mild and wet winter, and evergreen oak trees. Eastern China and the Atlantic coast are warm but wet in summer. Central Asia is dry but not warm. The combination of dry summers, wet winters, and drought-resistant trees like the evergreen oak points definitively to the Mediterranean region.
Let's look at two descriptive questions. In 2013, the prompt was, climate is extreme, rainfall is scanty, and the people used to be nomadic herders. Extreme climate with scanty rain defines the steppe, and nomadic herding is historically tied to the Central Asian steppe. In 2015, a passage described clear mornings, followed by mounting heat, dark clouds, and a short spell of afternoon thunderstorms. This daily cycle of convectional rainfall is the chief characteristic of the equatorial rainforest region.
Finally, a 2021 question described a biome where leaf litter decomposes incredibly fast, leaving bare soil, and where vegetation relies on climbing trees to reach the canopy or growing as epiphytes on upper branches. The presence of a dense canopy, epiphytes, and rapid litter decomposition due to high heat and moisture are all textbook features of the tropical rainforest.
To wrap up our study of cold climates, remember the key distinctions. The taiga, or continental subpolar climate, is defined by extreme temperature ranges, vast evergreen coniferous forests, and a massive lumbering industry. Further north, the tundra features permafrost, minimal vegetation like mosses, and a history of nomadic hunting. Finally, the polar ice cap is a frozen desert with permanent ice and zero vegetation. Understanding these climatic patterns is essential, not just for geography, but for understanding how human activities adapt to the extremes of our planet.